Look at any flight tracking map right now, and you'll notice something strange. Thousands of planes crisscrossing North America, dense highways in the sky over Europe, but right in the middle of the Pacific Ocean, almost nothing. A vast, empty gap stretching for thousands of miles. For an ocean that covers nearly a third of the entire planet, that silence is unsettling. Is it dangerous down there? Are pilots avoiding something? Or is there a rule, hidden deep in aviation law, that quietly decides where a plane full of passengers is allowed to fly and where it isn't? The answer isn't a conspiracy. It's not because the ocean is haunted, cursed, or radioactive, but it is one of the most fascinating, least known safety systems in modern aviation. And once you understand it, you'll never look at a flight map the same way again. Today, we're pulling back the curtain on why the world's busiest ocean has a no-fly zone right through its heart, why that emptiness is actually proof of one of aviation's greatest engineering triumphs, and what would really happen if an engine failed thousands of miles from the nearest runway. Let's start with the ocean itself. The Pacific isn't just big, it's almost incomprehensibly big. It covers more surface area than every landmass on Earth combined. Flying from Los Angeles to Tokyo means crossing roughly 5,500 miles of open water. Somewhere in the middle of that journey, a plane can be more than 1,000 miles from the nearest scrap of land in any direction. No highway, no hospital, no airport, just ocean in every direction as far as the eye can see. For most of aviation's history, that kind of isolation was a hard boundary, and it all comes down to one very simple, very human question. What happens if something goes wrong? Here's where the story gets interesting. In the early decades of commercial jets, regulators weren't worried about weather or turbulence or hijackings. They were worried about engines. Specifically, they were worried about what happens to a twin-engine plane if one of its two engines fails over open water. So back in the 1950s, a rule was created. If a plane only had two engines, it legally could not fly more than 60 minutes away from a suitable diversion airport, flying at the slower speed it would use with just one engine running. 60 minutes, that's it. Cross that line, and if an engine failed, the plane might not be able to glide, limp, or coast its way to a runway before running out of options. That single rule reshaped the entire map of global aviation. It meant that for decades, twin-engine jets were essentially locked out of the middle of the world's oceans. If you wanted to fly non-stop across the Pacific or Atlantic, you needed 3 engines or 4. Planes like the Boeing 707, the DC-10, and later the legendary 747 weren't just chosen for their size and range. They were often required because only aircraft with extra engines were trusted to survive far from land. But here's the twist most people never hear about. Those extra engines weren't really there for more power. They were there for backup, redundancy, insurance against a scenario nobody wanted to imagine, but everybody had to plan for. And for a long time, that was simply the price of crossing an ocean. Then, engineering started to change the equation. Through the 1960s, 70s, and 80s, jet engines became dramatically more reliable. The turbofan engines being built were failing far less often than their earlier counterparts. Engineers, airlines, and regulators started asking a question that would sounded absurd a generation earlier. What if 2 extremely reliable engines were actually just as safe as 4 less reliable ones? It wasn't a reckless idea. It was backed by mountains of data, stress testing, and years of real-world performance. And in 1985, the aviation world got its answer. A framework called ETOPS, Extended Range Twin-Engine Operations, was introduced, allowing certified twin-engine aircraft to fly beyond that old 60-minute limit for the very first time. That same year, a twin-engine Boeing 767 made history, flying a transatlantic route from Boston to Paris under this new approval. It was a quiet moment. No headlines about airplanes conquering the ocean, but it changed everything. Now, here's where a lot of people assume the story ends. Twin-engine jets got permission to fly farther from land, so problem solved, right? The empty middle of the Pacific should have filled up with traffic, except it didn't. And that's the deeper twist. ETOPS didn't remove the safety boundary. It expanded it. Instead of 60 minutes from a diversion airport, certified aircraft could now fly up to 90 minutes, then 120, then 180. Over time, as engines proved themselves even further, some of the most advanced aircraft flying today, like the Airbus A350, earned approval for up to nearly 6 hours from a diversion airport. But even that staggering number is still a boundary. It's not unlimited freedom. It's an incredibly precise, mathematically calculated leash. And when you actually plot that leash onto a map of the Pacific Ocean, something remarkable happens. The boundary traces a shape, a ring, bending around scattered islands, remote airstrips, and coastal airports, all connected by invisible arcs representing exactly how far a plane can travel on one working engine within its certified time limit. Outside that ring, in the deep, forgotten heart of the Pacific, nothing. No islands close enough, no airports reachable in time, a gap in the safety net that no amount of engineering has fully closed. That gap is precisely the empty patch you see on flight tracking maps. It's not because the ocean is more dangerous there. It's because, mathematically, there's simply nowhere close enough to land safely if something went wrong. But there's another piece of this puzzle that most people overlook completely, and it has nothing to do with engines at all. It's the shape of the Earth itself. We're used to looking at flat world maps, where the Pacific looks like a straight, wide-open stretch of blue between the US and Asia. But Earth isn't flat. It's a sphere. And on a sphere, the shortest distance between 2 points is almost never a straight line on a map. It's a curve, called a Great Circle Route. That's why flights from Los Angeles to Tokyo often arc northward, passing near Alaska and the Aleutian Islands, rather than cutting straight across the middle of the ocean. It looks like a detour on a flat map. In reality, it's the shortest, most fuel-efficient path physics allows, and conveniently, it happens to stay closer to strings of northern islands and airports the entire way. So the empty center of the Pacific isn't being carefully steered around by nervous pilots making last-minute decisions. It's the result of two invisible forces working together: the geometry of a curved planet dictating the most efficient path, and decades of aviation safety law dictating how far from land that path is allowed to drift. Which brings us to the moment this entire story has been building toward. Because there's still one question left unanswered. If a twin-engine plane really did lose an engine in the most remote stretch of ocean on Earth, what would actually happen? The plane would not fall out of the sky. A modern jet losing one engine can absolutely still fly, using its remaining engine to maintain altitude and continue toward the nearest certified diversion airport. Every single transoceanic flight plan already accounts for this exact scenario before the aircraft even leaves the gate. Dispatchers calculate precise alternate airports, fuel reserves, and diversion timing for the entire route long before passengers board. Remote islands, like Midway Atoll in the Pacific, have historically served exactly this purpose: a strip of runway in the middle of nowhere, existing almost entirely as an emergency option that pilots hope they'll never need to use. In other words, the empty patch on the map isn't a warning sign. It's evidence that the system is working exactly as designed. Every flight crossing the Pacific has already been mapped against this invisible ring of safety, engineered so precisely that the worst-case scenario has a plan, a runway, and a countdown clock built in before the wheels ever leave the ground. So the next time you glance at a flight tracker and notice that strange empty gap in the middle of the Pacific, you'll know the truth. It's not a place planes are forbidden from out of fear. It's the exact boundary of a safety calculation so precise it can predict, down to the minute, how far from land is still considered safe enough to cross. In an ocean that covers a third of our planet, that empty space isn't proof of what aviation can't do. It's proof of everything engineers have spent 70 years making sure it never has to.